In extension 2, there's a whole topic on proof that we're going to look at. Extension 1, I guess the key one that we look at is this idea of induction. So an inductive proof. So what's the logic behind it, the structure of it? Basically we have a series of statements, just like any proof really, but they're linked together using logical connectives, what we call logical connectives. So these are the pieces of the proof. Obviously, is there something we want to prove? That's a rather important part of the proof. We need to know what we're trying to prove. Some people call it a statement. So what statement with? Statement 1, some people write it as S1, I personally don't, to be honest. Proving the statement is true for the very first case, sometimes known as the base case. Then the next piece of it is an assumption. We assume that it actually is true for some generalized case. And then we go and prove it's true for the next case. But basically, using logic notation, that is an inductive proof right there. Now what does all that mean? Well, this symbol here, that's the symbol for and. And this one here is our implication symbol for if-then statement. So what we're really saying is, if we've got these two things, we've got the statement that we're trying to prove, we assume that to be true, and we've shown it to be true for the first case. If we have both of those things, then we can imply that it's true for the next case, which then means, oh, well, I've proven it true for all of them. And that's the idea behind induction. Let's put it together. How do we form a proof? There's certain steps. Now, you don't have to do step 1 first and step 2 second. You can actually reverse the order, because remember, they're just pieces of information we have to have. It just seems to be logical to do the first case first. So the first thing we usually do is go and prove the results true for whatever the first case is. The vast majority of the times that's just going to be n equals 1. It's not always n equals 1, but vast majority of the time it'll be that. Then we make our assumption. We're going to assume that the general case is true. Basically, it just matches whatever it is we're trying to prove. Now, just a bit of set notation. If you don't want to write where k is a positive integer, of course the shorthand way of writing that is where k is an element of the set of positive integers. So k is an element of z. I mean, it's a shorthand way of writing that. Then comes the proof. We're going to prove it's true for n equals k plus 1. Now, when you end off your proof, remember this is an if-then statement that you're proving, and that's what you write down. Once you've done your proof, you say, okay, what I've basically done is I've just proven it's true for k plus 1, but it's only true for k plus 1 if that assumption I made was correct, because if the assumption I made is not correct, my whole proof falls apart. And that's basically what this is saying. And that's why I've bolded this last bit. That's very important. I've proven it's true for k plus 1 if it's true for k. And then the last part is when you tie it all together and you go, all right, I've got the two things I needed now. I've shown it's true for 1. I've done my proof. If I pull that together, I say, well, okay, I've proven it's true for k plus 1 if it's true for k. But I've also proven it's true for 1. Well, therefore, it must be true for 1 plus 1. It must be true for 2. Now that I know it's true for 2, well, it must be true for 3. And that's what's called inducing the solution. Because then you can say, oh, well, that would just keep going on for every positive integer. And I guess a nice, neat way of writing that, rather than writing, oh, well, if it's true for 1, then it's true for 2. And if it's true for 2, then it's true for 3. And having to write all that down, we can simply say this. It's true for 1. Then it must be true for all integers. But those last 2 words are key. By induction. I'm inducing the solution. Let's do one. Now, when we looked at APs and GPs, we had nice, neat formulas to find the sum to n terms. This is not an AP or a GP. It's a different pattern. But there is a formula for it, and there it is. 1/3 n, 2n minus 1, 2n plus 1. So if we add up all the odd numbers squared, that's the formula. Well, let's prove it. I'll start off by proving it true for the first case. First case is when n equals 1. Now, as you know, I don't normally write left-hand side and right-hand side in things. This is the one situation where I will. because I'll say, right, I'm going to work on the left-hand side and see what n equals 1 is. So when I substitute in, I'll get 1 squared, which is 1. And now I'll say, well, what happens if I substitute it in on the right-hand side? On the right-hand side, I'll get a third of, and it's important you show your substitution, because if you were to simply just write left-hand side equals 1, right-hand side equals 1, oh, look, they're equal, that's not a real good proof. You show the substitution and show they become 1. But they are the same. So yes, I do know that the left-hand side is equal to the right-hand side. I've done that first piece of information, I know. So that, I mean, I wouldn't write that down, but I'm just pointing out that, okay, I've done the first case. That was one piece of information we wanted. And now we're going to write down our assumption, which essentially just matches what I'm trying to prove. I'm just changing n to be k. Now, and again, write down what you're about to attempt to prove. I'm going to attempt to prove it's true for n equals k plus 1. So this is what I'm now trying to prove. Basically, it's the next term, so 2k plus 1 squared. The right-hand side becomes a third k plus 1, 2k plus 1, 2k plus 3. Right? Let's do our proof. Okay, when you write down that left-hand side, you may not necessarily write that first line, you might go straight to the second line, but the second line is really important because it's highlighting something. What you've essentially got there is the sum of the first k terms, which is your assumption, plus the next term. I can now do the substitution. So that line there highlights, hey, I'm going to replace all of these terms because the plus dot dot dot. How can I play with algebra when I've got plus dot dot dot? I'm replacing it with something I can play with. And then I'd say, well, what I've done is I've used my assumption. Okay, so I did that using the assumption. Now, we know where we're trying to get to. Have a look at what we're trying to prove. Okay, it's something that's factorized. So don't waste time expanding this whole thing out. It already has a common factor, and one of those common factors is what we want. So it was stupid to expand the whole thing out only to refactorize it. The first thing I'll do is pull out that factor which I know I want. There's actually another factor already there. You might not spot it, but that other factor is 1/3. Okay? Look at what you're trying to prove. There's a factor of 1/3. Pull it out. That means this last bit, 2k plus 1, becomes 3 times 2k plus 1. Now, this last factor here of k, 2k minus 1, plus 3, 2k plus 1, that's what I want to show is the other two factors. It's just a bit of algebra. Now expand it out, factorize it, and we've got our result. That is what we were trying to prove. So hence I now know the result is true for k plus 1 if it is true for k. Some people like to write it down as if it's true for k, then it's true for k plus 1, because it is an if-then statement. Either way, it's just a bit of grammar, isn't it? Which way round you put it. So now we have that second piece of information we want for our proof. We have done the if it's true for k, then it's true for k plus 1. We've done that if-then statement. Pull it all together. Alright, well, since it's true for n equals 1, then I now know it's true for all integers, or all positive integers, by induction. Let's do this one. It's in some notation, but it's still a series of terms. You might like to actually write out them so you can see what the pattern actually is. But notice when I write it out, I don't write 3, 15, 35. I leave it as 1 times 3, 3 times 5, 5 times 7. So it sort of pulls the pattern out. I can see what we're doing. Oh, okay. It's 1 over, and then we're multiplying consecutive odd numbers. So 1 times 3, 3 times 5, 5 times 7, and so on. That's what we're trying to prove. We write that down. I'm going to prove it's true for n equals 1. Left-hand side, when I substitute in, we get 1/3. Right-hand side, 1 on 2 plus 1. Yes, that's also 1/3. Excellent. We've got our first case. We know that to be true. I'm now going to assume it's true for n equals k. Now I've written all the terms out. If you put it in some notation, that's where it gets a little bit awkward, because you'll be going k equals 1 to k of 1 on 2k. That feels a bit weird, so you might change the k in there to an r, or possibly it's just easier to write the terms out than try and muck around with some notation. I guess it just depends on how comfortable you are using some notation. We want to prove it's true for k plus 1. Alright, so that's what we're trying to prove. Let's do the proof. I'll rewrite it. So I got clearly what I'm going to end up substituting in for the assumption, so our sum to k terms plus the next term. Do the substitution. Okay, I got algebraic fractions. The answer I want is also an algebraic fraction. Make it all one fraction. Common denominator then becomes 2k plus 1, 2k plus 3. I'm heading to something which just has a denominator of 2k plus 3. This is one of the nice things about induction. Assuming what they give you is valid, you can sort of, well, not cheat, that's not the word I'm looking for, but clearly I know what the top of that is going to be. It's got to be k plus 1 times 2k plus 1. It has to, because then I'll cancel and give the answer that I want. So you can sort of cheat. But I wouldn't. I'd probably still expand it out, but then I'm probably not going to waste time and factorise because I know what I want. And I'll do it and go, oh yeah, okay, that now cancels to what I want. Mind you, the only drawback on that is if you make an algebraic error there and then you just go, oh, well, I know what that's going to be. Well, it's very easy to pick your proof and go, hang on, you've just fudged this to get what you want. Okay, but we do get k plus 1 on 2k plus 3, and that's what we're looking for. So, hence the result's true for k plus 1, if it's also true for k. And then we can induce it, tie it all together. So there's 3 key parts of our induction proof. The setup. Prove for the first case, we make our assumption, and then state what we're going to go and prove. So we're setting it all up. Then comes the actual proof. The proof itself is a deductive proof. It's an if-then proof. So just like any proof, we provide explanations for anything that's not obvious. Sometimes you think, oh, well, maybe substituting that assumption in was obvious. Yeah, possibly it is. Sometimes you rearrange assumptions to put it in and then it's not obvious. So it's not a bad idea to say, look, this is where I've used my assumption. But anything that's not obvious, how you jump from one line to the other, you should be explaining that. And then it is a proof. You have a conclusion. And for an if-then proof, you conclude with an if-then statement. It's a deductive proof. That third part, the crucial part, is tying it all together. How do these two things relate to each other to complete my proof? How do I induce my solution? So our exercise 2A, we've got some induction proofs.